solution exists for k greater than certain fixed number. This solution may not exist for small k. They only exist for large k. Okay, so for potential, so I have to consider those k which is greater than some fixed number. Okay, so this is one of the difficulties, but however, it can overcome. Okay, but here, from here, you can see that the f will become, so this integration will become 0. And in some sense, f is perpendicular to this expression, right? So what we're trying to do is we're trying to think about this as a function of k, like think about this function of k, and define the following. So suppose take this, okay? And then because this is for small k is not defined, so I need a cutoff function. So cutoff function, and in k, check the notation here. Is so multiply this by cutoff function with k greater than or equal to k. Then you can see this function is well defined for all k's, because for small k, it's just the 0. Okay, and then I take the inverse Fourier transform, because you can see without this remainder, this becomes the Fourier transform, right? I mean, without this remainder, these three terms, then this is just Fourier transform. Then you take inverse Fourier transform, then you get back to f itself. Okay. Now, but with the remainder, it doesn't matter if I take the inverse transform with it. So take the inverse transform back, you'll see this, the whole thing will become return to the function of x. Okay, but this function of x is not just defined on the domain omega, it's defined on the whole space, right? So therefore, I need another cutoff function with omega. Okay, so I make such a construction. They are going to consider map f go from here to here. This is a map. So the key is trying to understand this one. Okay. Now, exactly what happened, now think about it this way. Now, suppose we are dealing with zero potential. In the case of zero potential, the omega 1, omega 2 becomes 0. So this process, I mean, and you will back, basically it's a Fourier transform f, right? So now you can see that in this case, if you transform this back, the resulting function is going to be a part of f itself. Okay, so therefore you can see if in the potential 0, it makes sense to think about the f minus this. Okay, f minus that. Think about the zero potential case. Then without this technical cutoff function, then this whole process going from f to the inverse Fourier transform, then back to the f itself, then you subtract to the original f, you get what? You get exactly 0. Right? The 0 function. So you can see that you can think about in this case that f is when f is perpendicular to that, the f is going to be in the kernel of these transformations. So although this transformation is pretty complicated, but however I can rewrite this transformation in some simple way. I can split this into this way, f minus the first part. You take the f Fourier transform, then take the inverse Fourier. So this first part. Basically, this part corresponds to the function 1. Then the second part is the remainder part. Omega 1, omega plus omega 2 plus omega 1, omega 2. Then I'll split into two parts. Okay. And I'm going to call this the first part here is A naught. This A naught. Okay. This part is KQ. So the relation is like this. So they are all the linear map from L2 to L2. Okay. So you can see with this notation, you can see that this one imply that the K naught plus the A naught plus KQ apply to F. Equal to 0. Equal to 0. Okay. Right? So this F will become the kernel, inside the kernel of this linear map. And now the first way we're going to shoot is that actually the N naught is L2 omega to L2 omega. So this map is isomorphic. I mean, this one is going to be as inverse. Okay. Why is inverse? You look at this structure here. You know for the Fourier transform, we know that the F L2 omega F L2 is equal to the transform of L2, right? For the Fourier transform of the L2 space, why do you have that? So using this, you can examine this guy. Suppose. So A naught F equals 0. Then what can you say about F? So this means that F is going to be equals to chi K F this. Right? You're going to use that. Okay. So therefore, if you take the F naught, L2 naught, okay, then you can see that this will be less or equal than. I mean, using this identity, you can see that this has to be exactly will be less or equal than this one. Because you can see after the inverse Fourier transform, you multiply a cutoff function to get that. So if you put the result here, so this one will be less or equal than the L2 naught of this guy before taking the inverse Fourier transform. So this means it's going to be like this. Okay, right? But this one is actually also less or equal than. Now removing the cutoff function, the function getting smaller, right? Mm-hmm. Okay, so you can call this. And this one is equals to F. Okay? So you look at estimate. Using this definition, I can estimate from here to here. You can see this one is exactly equal to the same thing to the N. So this indicates everything in between has to be exactly equal. Must be equal, right?
Yeah.
In particularly, you can see this one. They're equal. But once this is equal, you can see this function, this cutoff function, is very different from the function here. So this means that this the Fourier transform of F is a function defined for each k, right? For all k. And then you remove all the large k. Then you look at L2 naught. But they're equal. The way they're equal, then you can see the only possibility is that the F inverse k has to equal 0 for k large enough, right? So the removed part has to be completely equal 0 in order for this L to not exactly equal. Otherwise, you always have another piece, non-zero piece, right? So what is exactly this indicate? Now think about that f is a function defining omega, okay? So before it takes the inverse, take the Fourier transform, the function is equal 0 outside omega. So you take the Fourier transform, that Fourier transform will be analytic. But for this analytic function, this function becomes 0.
0, okay.
So for like k, so the function has to be, the Fourier transform has to be exactly 0.
Okay.
So therefore the f has to be 0. So this shows that any f which in the null set of this in not has to be a 0 functions. So this in not has to be isomorphic from L2 to L2. And so therefore, you can see that the well, actually, when I say this isomorphic, actually I didn't skip one detail, because what we just assumed is this is what this is actually is injective, right?
Yeah.
In order for this surjective, what do we? So in order to become isomorphic, we also need to show that it is suggestive. But however, you can from the structure, yeah, here we have to use some fact, which we're going to use later. We will be able to show that this actually is a Fredholm operator. So this identity operator plus a complement operator. It's a complement operator. So therefore, and for such an operator, then if it is injective, will automatically imply it's isomorphic. I'm going to deal with that issue later. Okay, so don't worry about it. So what we're showing is here is that this is a isomorphism. So the inverse exists. If inverse exists, so I can multiply A inverse to it, right?
Mm-hmm.
So then you can see this things will imply that the I plus A not inverse AQ to the F. All right. Now this operator is better than previous. I mean, this is a identity map, okay? And here you have a combination of this map. So this is a bounded map, no problem. And then next, we're going to again skip a lot of detail. Well, we're showing that the KQ itself, KQ is compact. The KQ map is defined by the remainder here. It's compact. Now, if KQ is compact, then combined with A not inverse, this is a continued bounded map. So the combination will still be compact. Okay. So therefore, so this operator is identity plus the compact map. So this is called a Fredholm operator with 0 index. And this operator has a lot of nice properties. Okay, and from this nice property, well, there's a called more to say. Then you will be able to get these results. So I expect you to continue this next week after the first presentation.